Welcome to section 1.2 on functions. What is a function? A function is a relationship between two variables for which a unique value of the output variable can be determined from the value of the input variable. Now let's take a look at an example in trying to understand the definition of a function. We're going to do so by determining whether or not a function is being defined here. Our first relationship, we're going to have people as the input variable, and the output variable is going to be their birthdays. A person only has one birthday. So this is indeed a function since each person has exactly one birthday. Next, we're going to have fruit as the input variable, and the output variable is going to be its color. Well, can this be a function? Well, if we think about, say, an apple, how many colors can an apple be? Well, the most common color we know is an apple can be red, but quite often you can see green apples. You can also see yellow apples. So an apple can come in one of three different colors. Can this relationship be a function? No. Now, even though we used apples as the example, there are many different fruits that have several different colors. You could use any one of those fruits as an example as to why this relationship cannot be a function. Next, let's take a look at these tables here to determine whether these relations show a function or not. If we take a look at the first table, -10 is associated to 2, -5 is associated to 3, 2 is associated to root 5, 0 is associated to 6.3, 4 is associated to -0.2. Well, for each x, -10, -5, 2, 0, and 4, they correspond to one unique y value. So our blue table here is indeed a function. Now let's take a look at the orange table. Well, we have -4 to 3, -1 to 2, 10, 5, -1, 1, 4, 6. Well, I just said -1 twice. We see that -1 is related to 2, -1 is associated to 1. So my input value of -1 has two possible outputs, 2 and 1. So can the orange table be a function? No. -1 has two outputs. Now turning to the green table, we have -2, 3, -1, 2, 0, 5, 1, 2, 2, 3. Well, if we look, -2 is only associated to 3, -1 is only associated to 2, 0 is only associated to 5, 1 is only associated to 2, and 2 is only associated to 3. Is our green table a function? Yes. Now, one thing to be careful of when identifying functions is a common mistake is some folks would identify 2 repeating twice as an output variable and have 2 different input variables. This is okay for a function. We can have 2 different inputs have the same output. It's just that we can't have one input have 2 different outputs. In many different scenarios, you may have to work with either several different functions or plug in several different inputs into your function, or a combination of the two. To help communicate, we use something called function notation. Function notation is used to help communicate 3 things. What is the input and output variable? The relationship between them. What was the value of the input variable that yielded the value of the output variable? If x is an independent variable and f is a dependent variable, we will write this little notation here, which we're going to read as f of x or f at x. But seeing that notation, it tells us that our dependent variable is f, our independent variable is x, and that f depends on x. If we wish to assign x a value, let's say 6, and it turns out that f of 6 equals 3, meaning 6 is related to 3 under this function, by writing f of 6 equals 3, we are communicating that the value of f is 3 when x is 6. Now, in the next example, we're going to consider the following table. First, we're going to determine, does this table indeed show a function? Just because I have function notation here, the f of x, doesn't necessarily mean it automatically is a function. We should check first. While looking at the table, we can see that 0 is only associated or related to -79. 1 is only associated to 3, 2 to 2, 3 to 10, 4 to -1, 5 to 2, 6 to 34, and 7 to 2. You can see that for each possible value of x, the input variable, there's only one output variable it is related to. So indeed, this table does show a function. Now we're going to evaluate f of 3. This means we want to know, what does f equal when x is 3? Well, looking at the table, we can see that when x is 3, f is 10. So f of 3, according to the table, is 10. Next, we're going to find f of 6. F of 6 means when x equals 6, we want to figure out what the value of f will be. Going to the table, I see 6 right there on the table, and I can see that f of x will be 34 when x is 6. So f of 6 is 34. For what value of x does f of x equal 2? Now here, we don't know what x is, but we know f of x is supposed to be 2. So we're going to be focusing on the f of x row, trying to find 2. While looking at the f of x row, there I see 2. Well, what is the x value associated with this 2? Well, I can see that x is also 2. So f of 2 equals 2. So x equals 2 will be one of the answers. But is that the only time f of x will equal 2? You have to be careful with these kind of problems. When we're trying to find the x values that causes f of x equal a number, there can be more than one answer. If we look back at the table, we see there's a second occasion where f of x is 2. And what else causes f of x to be 2? Well, x equals 7. So there are two values of x that cause f of x to be 2. That's x equals 2 and x equals 7. In this example, we're going to take a look at how to use function notation when we have our function represented by an equation, and how we can use Desmos to help us evaluate functions. Let's consider the function f of x equals negative 3x plus 2. We want to evaluate f of 3. F of 3 is communicating that x equals 3, and we want to plug it into the equation that we're labeling as f. So taking a look at the negative 3x plus 2, anywhere that I see an x, I'm going to replace it with the number 3. We'll have negative 3 times, well, replacing the x with 3 plus 2. Now that I've replaced x with 3, I can follow order of operations. Negative 3 times 3 is negative 9 plus 2 is negative 7. Next, we'll evaluate f of 4, which means x is 4, and we're going to plug that into our function f. Everywhere I see an x, I'm now going to replace it with the number 4. We have negative 3 from the equation times x, which we're replacing with 4, plus 2 from the equation. Follow order of operations. Negative 3 times 4 is negative 12, plus 2 is negative 10. How can we do this a little quicker? Well, if we use Desmos, we can type in our function along with the function notation. From there, if I want to evaluate f of 3, I can just type in f of 3, and we can see here, f of 3 is negative 7. And I can do the same thing with 4. Type in f of 4, and I can see here, f of 4 is negative 10. Also use the table if we want to reduce our typing. We can create a table. In the first column, we can relabel it as x. The second column, we can use f of x, which is going to call upon the f of x that we entered. And we can type in any values of x we want, and we can see the table populates with the value of f of x. So f of 3 is negative 7, f of 4 is negative 10. When we're using Desmos to graph functions, we can think of f of x as being the y value. Any point on the graph of f of x is in the form of x f of x. If we're trying to solve when f of x is less than or equal to 8, we're going to enter y equals 8 as our second equation. And we do need the y equals to get that nice horizontal line. From my graph, I can see here that f of x is 8 when x equals negative 2. And by tracing along the graph, I can see that as x gets bigger, my f of x stays smaller than 8. More specifically, f of x is getting smaller. So from here, I can answer my inequality. We know x can be equal to negative 2, or it can be bigger than negative 2. When is f of x less than or equal to 8? That will be when x is greater than or equal to negative 2. There are often times where we're not just plugging in numbers into a function. We may be plugging in expressions. So for example, here, we want to evaluate f of x plus 2. Meaning everywhere I see an x in the negative 3x plus 2, I'm going to replace x with the expression x plus 2. Starting off by writing it out, the negative 3 times, well, x is going to be replaced with x plus 2. And then the plus 2, which was already part of my function. Start off by distributing in the negative 3. And we get negative 3x minus 6 plus 2. And then collect the like terms, the negative 6 and the 2, and we get negative 3x minus 4. Notice how I put parentheses around the x plus 2. The parentheses there are very important because that we're multiplying the entire expression x plus 2 by negative 3, since in the equation, negative 3 is being multiplied to x. Next, let's evaluate f of negative x. Just like with the previous example, we're going to replace x with negative x. We have negative 3 times negative x. Again, notice how I'm putting parentheses around the negative x. That way I know I'm supposed to be multiplying and not confusing it for subtraction, plus 2. Now that negative x is plugged in, let's simplify. Negative 3 times negative x. Well, negative times a negative is a positive. So we got positive 3x plus 2. There's no like terms to collect. So f of negative x is 3x plus 2. Even though Desmos can't evaluate f of x plus 2, we can still use Desmos to check to see if we simplified correctly. So going to Desmos, first I'm going to turn off the graph for f of x so it doesn't get in the way. And I'm going to type in what we got for f of x plus 2, which is negative 3x minus 4. And I can see the graph there in blue. In the next row, in row 3, we're going to enter f of x plus 2 with the function notation. Notice how the blue and the green lines are overlapping. That tells me f of x plus 2, negative 3x minus 4 have the same graph. They are the same exact value. So we simplify correctly. If I type in, say, negative 3x plus 4, they're two different graphs. Those are two different expressions. They wouldn't be the same. And the same thing goes with f of negative x. We can type in the 3x plus 2 in row 2. And in row 3, we can type in f of negative x. And again, notice how the two graphs perfectly overlap. That's because we simplified correctly. If we have a formula, we can always rewrite it in function notation. For example, here, the formula for the area of a square is a equals s squared. A is the area, s refers to the length of one side of the square. We're going to rewrite this using function notation. Thinking back to geometry, the area of the square depends on its length. So we can designate a as the dependent variable and s as the independent variable. So according to the function notation, a, which depends on s, so we'll replace a with a of s, equals s squared. Now that we would have it in function notation, we could use apps like Desmos to quickly evaluate several different areas given different lengths of a square.